So, good evening, everyone. Good afternoon. Welcome to the week 8th of this course, Principles of Modern CDMA, MIMO OFDM Wireless Communication of the tutorial session. So, today we will discuss the questions based on the week 8 lecture, and we'll also see some of the important formulas from the previous lecture. So, we'll start in 2 minutes. So, in today's lecture, we'll solve some of the questions based on singular value decomposition, then OFDM. So these will be the topics which we are going to discuss today. So just a minute, we'll start now. So today we'll start with the basics concepts of OFDM first, and then we'll solve some of the questions based on that. So OFDM stands for orthogonal frequency division multiplexing. So it is the basis of 4G wireless communication system. It stands for orthogonal frequency division multiplexing. So it is the basis for 4G wireless communication system. So basically, the OFDM is used in LTE, long-term evolution, and the WiMAX. LTE is widely used in 4G and LTE advanced as well. So the basic principles of this OFDM is to divide, like to transmit the multi carrier instead of single carrier. Like we'll see why this is required. So let's suppose the bandwidth of the carrier signal is, let's suppose this is the bandwidth and B is 10 megahertz. So this is the broadband signal. So now it is having the single carrier, and this is the carrier frequency, and bandwidth is 10 megahertz. So when we find the time duration, of this signal, we will get 1 by 10 megahertz. So this is equal to 0.1 microsecond. But the delay spread what we have studied is usually in the 2 to 3 microsecond. So as we can see, delay spread is much greater than the time duration, symbol time duration. So in this case, the inter-symbol interference occurs. Okay, so uh, like we know that this time duration is 1 by b. This is bandwidth. So if bandwidth decreases, then time duration will increase. Time duration of symbol increases. So we have to reduce the bandwidth. So how we can reduce? By by dividing into the multiple subcarrier. Okay. So now in this, let's suppose this is a bandwidth of 10 megahertz. So we will have multiple subcarriers. Let's suppose there is n subcarriers. Okay. So now bandwidth of each subcarrier, how much it will be? It will be b divided by n. Let's suppose this is b. So bandwidth of subband is equal to b divided by n. So let's suppose, so as example given in the class, let's suppose bandwidth is given as 10 megahertz and the number of subcarriers is divided into thousands. So this is the n, there is the n number of subbands. So now bandwidth of each subband is equal to b by n. So this will be 10 into 10 to the power of 6 divided by 1000. So what we'll get? We'll get 10 kilohertz. So now we will find the time duration. So we will get 0.1 millisecond. So that is equal to 100 microsecond. Okay. So now t is much greater than time delay. Okay. So in this case, symbol time is much greater than delay spread. So ISI, so no ISI is in this new system with multiple subbands and subcarrier in each band. So what is the advantage of this subcarrier? It reduces the symbol duration and sorry, it increases the symbol duration and that is much greater than delay spread. So in that case, the delay spread does not affect and therefore the inter-symbol interference is minimized. Now such system with multiple subbands and multiple subcarrier is known as multi-carrier modulated system. So this is the multi-carrier modulated system. So now we will see the our first question. So consider a bandwidth B is equal to 10 megahertz and number of subcarrier n is equal to 1024 in an OFDM system. Yeah, C is the correct answer. So now the OFDM symbol time without cyclic prefix, we'll also see about cyclic prefix later on. is approximately given as. So now the TS, what is asking in this question? The TS, the symbol time. Symbol time will be N divided by B. Okay, because T is 1 by B. So here there is N subcarrier, so it will be N by B. So in this case, our N is 1024 and B is 10 megahertz. So it will be 102.4 into 10 to the power of minus 6. Okay, so this is microsecond. Sorry, 10 to the power minus 6 second. So this we can write as 102.4 microsecond. So option C is the correct answer for this question. Now we will see the singular value decomposition in the MIMO system, because on that also there are some questions. So this SVD is required like when the channel is having R cross T, it is not a square matrix, and where R is greater than or equal to T. Even if it is square, we can use this technique. So if number of receive antenna, let's suppose this is our channel matrix and this is R cross T. So if number of received antenna is greater than or equal to the transmit antenna, so in that case, we can write H as U11, U12, URT. So here, like we can decompose the channel matrix with U, sigma, and V matrix, and this is the transpose of B. So we can give the transpose symbol here. So H we can write as U sigma BH. Okay. And here sigma 1, sigma 2, sigma t are known as singular value of the matrix. Okay, and these singular values are non-negative and ordered. This you write the note point. So these singular values are non-negative and ordered. So non-negative means sigma I is always greater than equal to 0, and ordered means sigma 1 is greater than equal to sigma 2, and this is greater than equal to sigma 3, and so on. Okay. So how to reduce the, like how to do the singular value decomposition of the channel matrix? So that we will see by taking an example from the classroom. So consider a 3 cross 3 MIMO system where H is equal to 2 minus 6 0 3 4 0 0 0 2. So here find the singular value decomposition of H. And there is one more part of this question. Um, so this is the first part. Second part is consider a transmit power of minus 1.25 dB and noise power of sigma n square is equal to 3 dB. Compute the MIMO capacity and optimal power allocation. Okay. So first what we will do, we will find the singular value decomposition of H. So H is equal to U sigma V Hermitian. And what is the property of the U matrix? U is U Hermitian, U will be the identity matrix. And similarly, V Hermitian, V will be the identity matrix. Okay. So our H is given as 2 minus 6 0 3 4 0 0 0 2. The first thing what we will do, we'll normalize each column. So first we will see the magnitude of this column. So this is square root of 4 plus 9, 13. So first normalize each column. So H will become 2 by square root of 13, 3 by square root of 13, Again now, the second column we have to divide by square root of 36 plus 16, 52. So minus 6 by 52, 52, 4 by root 52, 0, 0, 0. And this we can write it as 1 because it is divided by 2. So now we can multiply this at square root of 13, 0, 0, 0, square root of 52, 0, 0, 0, 2. So now these two, like multiplication of these two matrix will give us H. So we have just trying to figure out the U matrix. But here we can see the singular values are not in decreasing order because square root of 13 is less than square root of 52. So for that, what we will do, we will write it in decreasing order. So we will like exchange the column 2 with column 1. So we will get minus 6 by square root of 52. Just we are using the properties of matrix. So now we have to exchange the two rows here. So that will be, we will exchange row 1 to row 2. Again the multiplication will be same. But now it's not in the diagonal element. So what we will do, we will write H as, when we do the multiplication of these two, we'll get this matrix. Okay. So now this is our U, this is our sigma, and here also we can see root 52 is greater than root 13 is greater than 2. And this is our D. Okay. So this is the singular value decomposition of this channel matrix H. And also we can verify U Hermitian U, we will get I, and also V into V Hermitian we will get I. So now the second part of this question, that is consider a transmit power of minus 1.25 dB and noise power of 3 dB. Compute the MIMO capacity and channel optimal power allocation. So we will use the formula of capacity and also the formula of the power allocation. So that I will write it first. So we know that channel capacity is given as log 2 log base 2 1 plus SNR. Okay. So this is channel capacity. And for this, like we know that the SNR for the ith channel is given as sigma I squared P by sigma squared. So for uh, like sigma I is the gain of the ith channel. So for MIMO, the channel capacity will be, and this is also known as the Shannon rate. Shannon rate is the optimal channel capacity. So we can write C is equal to like capacity of MIMO channel log to the base 1 plus SNR. So that is sigma I squared T by sigma I squared. And this is like we'll optimize this. So this is optimal subject to the total power Pi is given as P. Okay. So we will use the constant optimization problem using Lagrange multiplier lambda. And then finally, we will get the power allocation Pi is given as 1 by lambda minus sigma. We'll write this formula in new page. The same formula we'll use for this question. So Pi is equal to 1 by lambda minus sigma squared by sigma I squared. Okay. If 1 by lambda minus sigma squared by sigma I squared is greater than equal to 0. Else it will be 0. So this we can find by like differentiating it with subject to the condition, like multiply the Lagrange multipliers lambda with the condition and then differentiate it and equate it to 0. Then we will get the like Pi. Okay, and also the summation of each power is total power is P. And this optimal algorithm like to achieve the capacity of the like maximum capacity of this MIMO system is termed as water filling algorithm. So now we can solve the question which is asked using these formulas. So here in this question it is asked, so these all are the sigma's values. So sigma I is equal to, first we'll note it down, sigma 1 is equal to square root of 52, sigma 2 is equal to square root of 13, and sigma 3 is equal to 2. So sigma 1 square will be 52, sigma 2 square will be 13, and sigma 3 squared will be 4. Okay, these are the three non-zero singular values. And what will be the rank of this matrix? 3, because it is having three non-zero singular values. Okay, so now the capacity C is given as log base 2 1 plus P1 sigma 1 squared divided by sigma the noise power plus 1 plus P2 sigma 2 squared divided by noise power plus, actually we are using the Shannon rate, that is log base to 1 plus SNR. So SNR is given as P3 sigma 3 squared divided by sigma n squared. Okay, so we will use all the value and the total power is given as minus 1.25 dB. So P is equal to 10 log 10 P is equal to minus 1.25. So it implies that P is equal to 10 to the power of minus 0.125. So this value will be equal to 0.75. Now, so total power P1 plus P2 plus P3 is 0.75. And what is the value of P1? P1 is equal to 1 by lambda. So we have studied this formula. Pi is 1 by lambda minus sigma square by sigma I square. Minus sigma square by sigma I square. Okay, Pi. So what is the value of this sigma n square? So this is given as 3 dB. So 10 log 10 sigma n square is equal to 3. So sigma n square is equal to 10 to the power of 0.3. So this will become 2. So our P1 plus P2 plus P3 we can write as 1 by lambda minus 2 by 52 plus 1 by lambda minus 2 by square of square root of 13, that is 13, plus 1 by lambda minus 2 by 4. And this value is Pt. Pt is given as 0.75. So now we can do the summation. 3 by lambda is equal to 0.75 minus 1 by 26, sorry, plus 1 by 26 plus 2 by 13 plus 1 by 2. So we will get lambda is equal to 0.75 plus half plus 2 by 13 plus 1 by 26 divided by 3. So 1 by lambda is equal to, when you solve this, you will get 0.48. So now what are the values? P3. P3 is equal to 1 by lambda minus half. So that is 0.48 minus 0.5. So this is minus 0.02. It is less than 0. So here in this case, P3 is equal to 0. Okay. As we have already studied. So now we will set n is equal to 2 and then we'll solve the question. So 1 by lambda minus 1 by 26 plus 1 by lambda minus 2 by 13. This is equal to 0.75. So now again we'll find 2 by lambda is equal to 0.75 plus 1 by 26 plus 2 by 13. So lambda will be this time 0.471. So now P1 is equal to 1 by lambda, sorry, 1 by lambda minus 1 by 26. So now this time it is greater, because 1 by 26 is less than 0.47, and P2 is equal to 1 by lambda minus 2 by 30. So both are greater than 0. So when we find that P1 is equal to 0.4327 and P2 is equal to 0.3174 and P3 is equal to 0. So we can find it in dB also. So 10 log 10 P1, when you do this, you will get the value somewhere near minus 3.63 dB. You can do this calculation. And 10 log 10 base P2, we will get as a minus 4.98 dB. Okay. So now the channel capacity C is given as log to 1 plus P1 sigma 1 squared sigma n squared divided by log base to 1 plus P1 sigma 2 squared by sigma n squared. And we will not take the third term because P3 is 0. So log base to 1 will become like 1 plus 0. So it will be 1. So that value will equal to 0. So finally our C we will get when you find this, like substitute all the value. So we have all these values. Log to 1 plus 0.43 into 52 by 2 plus log 2 1 plus 0.31 into 13 by 2. The final answer we will get 5.23 bits per second per hertz. Okay. So this is also the unit of capacity, that is bits per second per hertz. Now we'll move on to question number 2. So in this question, it is asked, consider a OFDM system with channel taps H0 is equal to 1 plus 2j, H1 is equal to 2 minus j, and N is equal to 4 subcarriers. So the coefficient H3 for k is equal to 3 is given us. So we'll use the formula. It will become H0 plus H1 e to the power of minus j2 pi, and here k is equal to 3 and k by n, so n is equal to 4. So now we can substitute the value minus 3 pi by 2. So this value will become j. We will get H3 as 1 plus 2j, 2 minus j into j. Minus j squared will become minus of, so plus 1. Will become 2 plus 4j. So option D is the correct answer for this question. Now moving on to the question number 3. So consider a OFDM system with noise power sigma squared is equal to minus 3 dB. Number of channel taps L is equal to 16. Number of subcarriers is 1024. And transmit power P is 30 dB. Now if each channel tap is IID relay with average power 3, and that is what will be the hello what yes. So now in this question sigma square is given minus 3 dB, so we can find into the 10 log 10 sigma square is equal to minus 3. So we'll get sigma square is 10 to the power of minus 0.3. So this is 1 by 2. Again transmit power is 30 dB. So 10 log base 10 PT is equal to 30. So transmit power is 1000. Expectation of mod of HI squared is given as 3. So we have to find average output SNR. So average output SNR will be expectation of HK squared P divided by N sigma squared. So now, so there L is equal to 16 like channel tap. So here it will be E of HK squared will be summation of 3 I is equal to 0 to L minus 1 multiply with P and sigma squared. So this will become 3 and into L times, so 3 LP divided by n sigma squared. So we can substitute all the values. P is 1000, n is 1024, and sigma squared is half. So we'll get 93.75, and we can also find it in dB. So that is 10 log 10, 93.75. So this will be equal to 10 into, and this value is somewhere less than 2. So it will be 1.97. It is 19.7 dB. So we have this option A is the correct answer for this question. Now consider a zero padded OFDM system in which the cyclic prefix is replaced by zeros, and the frequency selective channel has the channel taps H0, H1, H2, and H3. So the number of subcarriers equal to n, and zero padding is of length 5. So we have to find the output symbol y1. So y1 will be h0 x0, then it will be h1, sorry, h0 x1, it will be first one, then h1 x0, and then before like x1 x2, like that. So before this there are zero padded. So now whatever we multiply h2 into 0, h3 into 0. So our y1 will be h0 x1 plus h1 x0. Okay. So the correct answer is option number C. Now this is simple question. What is the approximate data rate of LTE? So this we have studied in the first lecture. It is around 100 to 200 megabit per second. So now which operation is employed in the receiver of the OFDM wireless system? So at the receiver end, the fast Fourier transform is applied, and at the transmitter end in IFFT is applied. So this is applied at the receiver end, and this is applied at the transmitter end. So this question is asking at the receiver, so it will be FFT. So basically, this we can represent with a diagram. So let's suppose like the symbol is given x0, x1, x2 dot dot xn. So initially we give it into the demultiplexer, serial to parallel demultiplexer, and then we do n point IFFT. So now here we receive x small x0, x1 dot 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 xn. So now again parallel to serial multiplexing, and then a cyclic prefix is added, and then it is transmitted. Okay, TX. So this is the OFDM transmitter diagram. Now at receiver, it is again simple only. So we will do everything in the reverse way. So first, let's suppose this is our receive antenna. So first we will remove the cyclic prefix. So this is the receiver RX, and then again we convert the data from serial to parallel. Okay. Now we will do n point FFT. Initially it was x0, x1. So this will become the frequency term xn. Now uh, the parallel to serial multiplexer, and then this is given as uh, so by this way we can receive our signal back. So this is the receiver architecture of the receiver in the OFDM. This I have drawn the rough diagram. You can go through the lecture. So there it is drawn everything properly. So now we'll move on to the seventh question. So consider a bandwidth B is equal to 10 megahertz. I think this is the repeated question. No, it is different. N is equal to 1024. Actually, only the cyclic prefix is added here. So let the cyclic prefix contains 256 samples. Okay. So now, so cyclic prefix contains 256 samples. So in this case, we'll have total number of samples including cyclic prefix will be 1024 plus 256. So this will become 1280. So now the symbol time is equal to 1 by B, and OFDM symbol time with cyclic prefix is given as total number of sample divided by bandwidth B. So total number of sample is 1280 divided by B is given 10 into 10 to the power of 6. So this will become 128 microsecond. So option number B is the correct answer for this question. The next question is OFDM is used in which of the following wireless standards? So this WCDMA HSDPA used in 3G, GPRS is used in 2G. So WiMAX is the correct answer. Okay. Coming to the question number 9. Again, it is similar question what we have solved in the beginning. Consider total transmit power PT is given as 3 dB. So when you convert normally, we'll get PT is equal to 10 log 10. PT is equal to 3. So PT is equal to 10 to the power of 0.3. So it will become 2. Sigma squared is again 3 dB. So sigma squared will also become 2. And the singular values are given as sigma 1 is 1 by root 2 and sigma 2 is 1 by 2. So what will be the what is asking the optimal power values for two singular modes are. So P1 is equal to 1 by lambda minus sigma square by sigma 1 square, and P2 is equal to 1 by lambda minus sigma square by sigma 2 square. So we'll use the same formula, and P1 plus P2 is equal to 2. So 1 by lambda minus 2 by 1 by 2 plus P2 is given as 1 by lambda minus 2 divided by 1 by 4, and this is given as 2. Or 1 by lambda is equal to 7. So P1 is 1 by lambda minus 4, so that is equal to 7 minus 4 is equal to 3, and P2 is equal to 1 by lambda minus 8, so this will become minus 1. So again this is 0. So now what we will do? We will remove P2 and do with only P1. So P1 is equal to, only there is one power, so P1 is equal to 2, that is equal to PT. Okay, because P1 plus P2 is equal to 2, and if P2 is 0, so then obviously P1 will be 2. So the optimal power values are 2 comma 0. So option A is the correct answer for this question. So just a minute. So now we'll move on to the next question. So consider an OFDM system with channel taps H0 is equal to 2 minus J and H1 is equal to minus 1 plus 2J and N is equal to 4 subcarriers. So we have to find H1. So basically we'll use again the same formula. So HK, so I'll write the formula. So this is basically HL e to the power minus J 2 pi KL by N. So here K is given as 1. So H1 is equal to and H0 is 2 minus J. And when we substitute here K is equal to 0, then this value will become, sorry, L is equal to 0, this value will become e to the power of 0, this is 1. So that's why 2 minus J plus minus 1 plus 2J e to the power of minus J 2 pi. K is 1, L is 1 divided by 4. So H1 is equal to 2 minus J plus minus 1 plus 2J e to the power of minus J pi by 2. So this will become 2 minus J minus 1 into minus J to become plus J minus 2J squared to become plus 2 to become 4. So the correct answer is option number B. So for today's week, like these were the questions. Okay. So we'll look into that. Yes, yes. So basically in OFDM, like what we have studied, it's a multi-carrier modulation scheme. So we can write like the transmitted, like as taught in lectures only. So the transmitted symbol is given as xk e to the power of j 2 pi k f naught t. So, so this is our signal transmitted on the kth subcarrier. So there will be like in the bandwidth b. So there will be different subcarrier. So for the kth subcarrier, the signal transmitted will be xk e to the power of j 2 pi k f naught. Okay. So like here sk is the kth symbol, and the signal transmitted is given as skt. So now like the yt is given as summation of xk e to the power of j 2 pi k f naught. So this is our received symbol. Okay. So this is similar to like Fourier series, and we can go through the diagram. So let's suppose we have to extract the symbol on the kth subcarrier. So in that case, what we can do, like to extract the symbol, xi, let's suppose on the ith subcarrier. So this we can write it as e to the power of minus j 2 pi I f naught t multiplied with yt dt. So we can substitute this value of yt, and then we will get summation of like xk will come out. This integration is 0 to 1 by f naught e to the power of minus j 2 pi I f naught t, and into e to the power of j 2 pi k f naught t dt. So here the term will come as e to the power of j 2 pi um, f naught t we can take common. So here we will get k minus I. Okay. So now if k is equal to I, then this term will become 0, and the complete this term will be 1. If k is equal to I, so this term will be 1. If k is not equal to I, so this term will be 0. So to receive the ith symbol, we have to correlate with the e to the power of j 2 pi I f naught t. So this is one of the thing, and the second what I have shown the diagram. So this is enough to understand. So here first as you can see, this x naught to xn. So these are the transmit symbol, and then the IFFT is required at the transmitter end, and then this and after that it is transmitted on the receiver end. We have to use FFT. So these two are the important thing, as you can see in OFDM. And also to reduce the to reduce inter-block interference, a cyclic prefix or the zero padding is used. So these things are important in the OFDM. You can go through the lecture slides, so all things are explained. Basically, with correlation of the th or ith subcarrier, we can receive that symbol.
Sir, only the last week the video only the link was available. Video was not available, sir.
Yeah,
Recording.
that link is rectified. So now that video is available. Actually, that got corrupted. So I have again uploaded and changed the link.
Today's video will be
So today video I will upload now only, like
okay.
after an hour. And also like you can go through all the lectures. The slides is also available there. So like we can see once we can scan through all the slides. Uh, or better you can go through these slides. If you have doubt, you can ask in the forum. So you can go through the important formulas which are discussed in the slide. So those formulas are used to solve the questions of each week assignments. So I have discussed some of the concepts and formula in each week. So you can go through each of the slides as a note, and also like if you have any doubt, you can ask on the forum as well.
Okay, sir.
So thank you for today's class. I will upload this video now only. So thank you everyone.
Thank you.